Okay, let's go ahead and keep going. So, pipelining is a pretty important feature in computer architecture because everything performance-wise continued from standard pipelining, from which we're doing in order today, all the way to out of order, which we won't cover in this class in any depth, but we'll at least talk about it somewhat.
Oh, why not?
Well, just take a master's and we'll do out of order execution. We'll be good to go, okay?
Okay.
You could at least sigh louder. There we go, because the mic has to pick it up.
There we go.
All right, good
I
job.
think the mic would pick it up quietly too.
All right, well,
Like,
someone
I
can
am
report.
on the mic right here.
Well, I'm sure someone will report back. David, that's your homework. Tell me if the mic picked it up.
Oh yeah, I mean
The
it picks
first
up,
side,
it picks
not the
up
second
everything.
side.
Okay,
over
good.
there.
That's good. So this was single cycle. What's wrong with single cycle?
it only works once.
It only works once?
It only does it once. It's very hard to implement multiplication.
No time.
No, you can implement multiplication. That's not a problem.
It just takes longer. And
Oh,
it relies on the
Time.
longest
Yeah, what's
thing.
the timing problem, guys?
Well, it's obviously too
Ridiculous.
slow.
It's slow. Why is it so slow? Yes, Dave.
Jonah will be here at 8:18.
Cheater.
I hope you're wrong. I hope I am.
I hope he's wrong. I hope it's 8:20.
Me too.
It's actually gonna be 8:19.
You watch. Because what he told you is probably a lie as well. Anyways, so what's the problem? You add multiply and what happens?
It slows down.
It slows down. What does it slow down?
The whole thing.
The whole thing. Why does it slow it all down?
Because it relies on the slowest instruction.
You're right. So the slowest instruction dictates the entire clock cycle. All right. So we need to come up with ways to alleviate that problem. We first came up with multi-cycle, and the idea here was you would at least break it up into fetch, decode, and execute, and each of those would be their own cycles. Execute could take multiple cycles if it needed to, but fetch and decode would still be the same. That way you can at least have more complex instructions without making all instructions slower. All right, we did the whitewater rafting analogy. Do you all want to do it again? You do? Okay, great. So rafting in the 70s, this was like a single cycle. You find an old surplus raft, army raft, because apparently the Navy doesn't have them. Find a river, you put raft in river, float to the end, you get out.
The Navy doesn't have them, they have boats.
They have
No,
both.
in the Navy, they're not surplus, they're still using them. You're using life raft.
Yep.
Yep, they're still using them. Oh, okay. Number of people on river, 1. Resource allocation, 1 person on river until done. Okay. And apparently you get this pelican.
So there's two
Quite
people.
nice pelican.
Cute.
No, the pelican's not a person,
I
man.
mean,
It's cute.
There's also
Find a
brown.
person.
I've never
There's
seen a brown
like
pelican.
pelican.
Fire pelican.
There's brown pelicans.
I know, it's just I've never seen one.
So you build a processor, find an instruction that you found on the side of the road, put instruction in processor, run the instruction, and get out for the next. So this is the single cycle. All right.
Get out.
Get out. Multi-cycle. Apparently this is like the 80s. You find a new rafting company because they're new. Pay your fee for a boat and guide, line up the rafts on the river, float in line to the end, get out, make the guides clean up. So the idea is you might have 20 or 30. You could have 100 people on the river in a day. This was a little more like pipelining, which is what we're talking about. Well, actually it's more multi-cycle, I like. Build a processor, line up the instructions. So you have fetch, decode, fetch. And this is pipelining, so it is, yes.
you can change mine to 8:12.
It's,
I did put 8:10 on first.
I
I'm
put
leaving
8,
it.
10.
I am leaving it.
Sorry, let's keep going.
So the point of this is what happens to your CPI as you are pipelining. What is CPI?
Computer processing instruction.
Say that again?
Computer processing instruction?
All right, so you got the last one correct.
Cycles
Okay,
per
There we go, cycles per instruction, right. So do
Something
you want
with
this?
a computer.
Do you want this number high or low?
No.
High.
Low.
Low.
This is just not a good class for you.
No. It is low.
Never-
I remember why.
All right.
You want as little cycles as possible.
And hopefully CPI will approach 1 because hopefully you'll be able to retire or complete a cycle complete
One
an
and done.
instruction every cycle.
Yeah.
Yeah. The 90s is when we started setting up a lot of pipelines, and you'd actually do out of order execution because you might have multiple rafting companies on the river that might be going in at different points, kind of like a freeway, and might be exiting at different points, kind of like a freeway. In which case you might have 200 to 500 different people on the river. Maybe you still have the good old surplus army raft in there. And then you have, lots of people on the river.
What's with the blue shape?
The which one?
The blue shape in the
It's supposed to be the river.
That's the river.
Oh, that's the river? Okay. Now that makes sense.
Wait, go back. What's the one at the bottom? Oh,
Those
those
are
are all
boats.
the empty rafts, I guess.
They're boats. Little dinghies.
All right, execute to as many instructions at the same time. Pipelining in this case, we only talked about 5 stage, but you might have 12 to 20 cycles.
813.
8:13.
Dang.
Wow.
Who's it? Okay, so 810 was right.
So,
Ah! That's closest.
nope, can't go over.
So who said
That's over.
That's over. Wouldn't it be 810?
Yeah, it has to be 810.
Oh, I'm sorry, you're right. Can't go over.
I win.
8:10 1. Wow.
Who said it? Oh, you said 810?
I win.
Dang. The person who had the most faith.
Yeah, wow. Person had the most faith won. Sorry, $1. It's okay.
See, 8:15 was real close though. 1 minute.
1 minute would be close.
Nah, 8:10 is closer.
I win.
Thank you, Jonah.
I had faith
Just
in you.
saying.
So was the $1 just for the $1 guy, or was it for just?
$1 means he thinks that he'll come in before everyone else has voted.
Yeah.
Good job, Jonah.
Hey, I'm happy whoever got $1. I don't know who got $1.
I don't know who win. I don't know what
Got
money
you
we're
$1.
I don't
getting.
know who won, but I got you $1. You're welcome.
Just by showing up to class.
Yep.
At that specific time.
You might have multiple pipelines running at the same time, so you can execute multiple instructions at the same time. The Pinium was 2 pipelines, 5 cycles each. And we're going to kind of get to what a Pinium did in our in-order pipeline. The Pinium Pro is when they went to out-of-order execution, and if you take my graduate class, we'll learn about this.
Whoa.
But you would have multiple instructions in flight or executing at the same time. And the Pinium 4 went crazy with 4 pipelines, 20 cycles deep on each pipeline. All right.
Well, it turns out I actually read Richard's message, so I guess you didn't text me.
No, I did. I said I was
Well,
here.
yeah, you once. I realized I'm like, oh,
And what has that taught you? David,
not
not to cheat. Thank you, David.
It's that walk, man. I'd be here like 10 minutes earlier every day if I didn't have to walk a
Dr. West
freaking
is
mile
now
all the
actually
way
forgot
over
my
here.
real name. I'm just David.
Yeah, I call him, well, it depends on the situation.
Yeah.
David.
Yeah.
All right, so we're going to do pipelining of our MIPS 32 instructions. We're going to try and keep it simple because, as you've noticed, things get complicated very quickly. But we want to break up the execution of instructions into multiple cycles, similar to multi-cycle, except we want to design a separate data path stage for each execution performed during each cycle. And so we're going to complete part of this instruction and then wait till the next cycle to do the next section for the instruction. In order to do that, we have to somehow save the state between the first part and the next part, the second part, the third part, the fourth part, and so forth. So we save the state in what's called a pipeline registers. All right, stage 1 is fetch. There's going to be 5 stages in total. I'm going to go through each one. The idea is that we want each stage to be very, very simple, and then we're just going to save all the information we can at the end of the stage. So stage 1, fetch. We're going to design a data path that can fetch the instruction from memory and then save it. That's all it does. It doesn't do anything else. Well, okay, I lied. It increments BC, so it knows what the next instruction to fetch is. And then when it's done, it's going to save everything into a pipeline register IFID, aka instruction fetch, instruction decode. This is the pipeline stage between fetch, which is stage 1, and decode, which is stage 2. Everyone got the pipeline register? All right, so it starts to look like this. Yeah, diagrams are nice, aren't they? PC is a register. We have to enable it in case we want to override it. We have instruction memory. We're going to read from instruction memory the address at PC. And what do we need to do with that instruction?
Save it
Save it where?
in the pipeline register.
Yeah! Okay, first we have to increment PC. I lied. Alright, there we go. Can we save it? Alright, we do have to increment PC to PC plus 1. And we have this mux, but we're probably going to select increment PC to PC plus 1. Why do we have a mux?
To select stuff, but we're-
Yeah, what are we selecting? We're selecting between PC plus 1 and
Not. Oh,
PC?
branch.
the branch target. In case we change the branch, we need to use the branch instead of PC plus 1, right?
Yeah, but it said
Yeah.
Well,
earlier
there's
we're
only
not
one
to
thing
do the
going in the
branch,
mux
so.
right now.
What's that?
There's only one thing going in the mux.
Well, we store PC plus 1, and then remember the blue line?
The
Yeah,
branch.
the blue line. Yep,
Branch.
branch. Any questions on this picture? Good. I'm glad this is a review.
I like
So
reviews.
decode, yeah.
Yeah.
Yeah. So decode, we have two things going to decode. What are the two things going to decode?
Oh, the instruction,
The instruction bits and the PC plus 1.
Everyone got it?
Yeah.
All right.
Whoa.
All right. So we're going to read IFID pipeline register, aka the instruction bits and PC plus 1, and then we're going to read the contents of register A and B, and then store them. Yeah, that's it. And then pass along PC plus 1. That's all we're going to do. So here are the instruction bits. We have to read to the register file, and where does the output go?
Into another register.
Into another pipeline register. Notice this one is labeled instruction decode / execute because it's a pipeline register between decode and execute.
Whoa.
Everyone got this?
Whoa.
I get a lot of questions about this. The pipeline register is just storing the state in between the stages. All right, what else is in this picture?
Branch.
The number of pipeline registers is equivalent to the number of stages then?
-1.
Minus one. Oh,
Yeah, because you're between the stages.
Minus.
So we have 5 stages, and there will be 4 pipeline registers. All right, what else do we need to do?
Branch.
That's true. We'll get to the branch in a moment.
The other two that go into the register file. I forgot their-
Oh, wait, PC plus 1. Where does that go?
Where does PC plus 1 go?
Register file?
no.
Or no, does it go straight over to
Goes
the
to
next
mux.
pipeline register?
Mm-hmm. What else do we need?
Oh, then.
The branch.
Branch, but what else goes to the next pipeline register?
Ooh.
Ooh. The instruction.
The instruction, yes.
Oh.
Did I get this?
Right.
Everyone get so far?
Do you
All
have
right.
it?
And now someone said the branch goes back. That's
Yay.
true. And what else happens?
The other two things.
No, we don't care about. Well, we already stored off the PC counter up here.
We're
Those are
running
the
out
two
of
lines
space.
yet?
Hmm.
The other two lines yet?
There's 2 other blue lines. Actually, I think there's 3.
They go into the register.
Yeah, they go into the register file. Yeah. And that's in case we need to write to the register file. We haven't written anything yet because maybe an instruction further down the pipeline need to register or write to the register file. How's everyone doing? Okay. So we're going to go to execute. Before I click to that slide, what are the 4 things execute has before it starts?
Those things.
Instruction bits.
Whoa.
The
Those.
registers.
The contents of register A, register B, and
PC plus 1.
so with those pieces of information, it's going to do the execute stage.
Yeah.
Design a data path that performs the standard ALU. What's ALU stand for?
Arithmetic logic.
There we go, arithmetic logic units, where you do your add, your nands, or whatever else you want. For the instruction specifying the values present in the IDEX pipeline register, what is that register?
That is the decode and
The
execute.
register between the decode and the.
Execute.
Okay.
I'm only doing this because I get a lot of questions about the pipeline register. All right, the inputs are the contents of A and B and the offset field in the instruction, because you got to read from the instruction and calculate PC plus 1 plus offset in case this is a branch. Write everything needed to complete execution to the next pipeline register. So it's just doing math. I mean arithmetic, which is not math. Trust me. All right, so we have this. What do we need to do?
Execute.
Who are we executing? I mean, what are we executing?
With the ALU, you have to take the contents.
Wait.
A little louder, please, Jonah. I don't know if my mic quite heard that.
No. I didn't say anything.
All right, so register A goes to ALU and B goes to it. But why do we have a green line?
That's blue.
Are you okay, man? Do you need a hug?
Yeah.
He doesn't want it from me. I just told him I'd execute it.
Gosh, Jonah.
Wouldn't
You
that
can't just say
instruction be
that.
called what type of arithmetic?
Arithmetic, yeah, let's go there. But why do we have something from the instruction bits going to the mux, which then goes to ALU?
What if register B had nothing?
That's true. What if the instruction wanted to use the offset field of the instruction bits?
And you would want to ignore it. Register B.
Yes. All right. Oh yeah. What do we store in the ALU? Hey, look, the ALU result. There, I gave you
Whoa.
one. All right. What else needs to be stored?
PC.
P.
P plus 1.
You're close. PC plus 1 plus
What?
One. Offset.
offset,
Offset.
in case it's a branch.
And-
Okay, we need contents of
oh,
register B.
Yeah, that too.
Why do we? But here's a good question. Why do we need the contents of register B but not register A?
Because A is part of the ALU.
Okay, sure.
A is part of the ALU results, and B is not necessarily.
Correct. But what instruction later on? Okay. After execute comes memory, and so if you are storing to an address, register B is going to tell you what that is, or your destination of an instruction, like if you're doing add, I mean not destination, sorry. If you're storing, you need the contents of register B, is what it comes down to. So you know what to store.
Oh.
All right, so
You
then
need
we
the
have
instruction bits.
PC plus 1 plus offset and
The instruction bits.
the instruction bits.
Yeah.
Yay. All right, what are we missing?
Range.
And
Register.
the register stuff.
Yeah.
Okay, so over here we have the execute mems pipeline register, which means the contents of this will be sent to the memory stage. So the memory stage is going to have what in order to execute?
Instruction bits. Contents of register B. ALU results. And PC plus 1 plus offset.
All right, good. Any questions?
Oh, pick.
All right.
All of the pinks on the right side of the screen.
So memory, basically, let's go ahead and implement load and store. Opcode bits are going to control what the read, write, enable signals are. Write everything needed to be completed to the last pipeline register, which is memory and write back. Okay. So we have this stuff. What do we do?
Something with memory.
Something with memory. Good guess. Well, we actually forward the LU result.
JK.
What?
I said JK.
Yep. Anything else? You said memory. Maybe the next one will be memory? Oh, good.
Mm.
So ALU result and contents of B. Well, if it's a load, then you take the ALU result, read that memory, and then the memory read comes out there. If it's a store, then you need to send the ALU result, which tells you the address you're storing the contents of register B into. All right. What else are we missing?
Instruction bits.
Okay, instruction bits.
And the PC plus 1 plus offset.
Now, hold on a second. Good guess. But we're not forwarding that anymore because
You're using it.
we're going to use it and hopefully send it back to that mux at stage 1 in case we need to change it.
And
Because
those other two things from the data memory go all the way over to you.
not quite.
No?
Nope, those are the next
Oh.
one.
They're
That's the next
forwarded
one.
over here. Because remember, this is going to take a whole cycle to complete. While this, we already have the information, so you might as well just send it back.
Okay.
But now determining which, if we're gonna use it or not, the branch, we would have to send the instruction, or would it already have it at the months for the first time?
That is a great question. We'll get to that in a couple more slides.
The world may never know.
What else are we missing?
The other two lines.
The two blue lines. Keep in mind that the top one always goes under the instruction bit here and over the. All right.
That's
Nice.
you some.
What?
No, that doesn't make you so bad.
By the way, that's a joke for everyone online.
Future us.
Okay, so this is the memory write back pipeline register because it's going to store all the contents needed for for write back. So the write back stage, what does the write back stage have?
Instruction bits, memory data, and LU results.
That's it. That's all it has. All
Magic.
right.
No, the controls, the enable and read write, that's coming from
The instruction bits.
at the very beginning, or?
Yeah. Well, no, right here from
Right
this
here.
pipeline register.
Those are
Yeah. The thing is,
online videos,
at the
which
stage,
really
it all
lost.
between each stage, it only knows what's before
So
the
it is
pipeline.
actually connecting to, I mean, as
Yeah.
going off there.
Yeah. You have your logic right here to figure out which of these should be enabled and which should be read and write. Yeah. Good point. Good point. Keep that in mind. That you're just reading from the instruction bits of the previous pipeline register to figure out what it should be. All right. Write back. This is where you actually finally, hey, write the contents back. So if it's a load, you write the memory data to destination register, write the ALU result to the destination reg for add or NAND, and op bit are used to control what registers write signal. All right, here we go. So we have mem write back pipeline register. Do we have an ending pipeline register?
No.
No, because this is the end of the pipeline. What do we do first?
It's hard.
And hair.
I can see that.
What was the question?
Remember the instruction has to.
Mux.
What are we using the mux for?
But isn't the.
To select between memory read data and the ALU results.
Yeah.
Why are we doing that?
Because we want to.
Wouldn't technically the first thing they do would be to take the instruction bit and find out what you're actually doing at each time?
Sure.
I mean, so with the
Yeah,
control line.
your instruction bits would select which of these two muxes or which of these two inputs are going to go back to the register file, the ALU result or the read
Right.
data, aka is it a load or not a load. And then here we have, because with a load, your bits that you're loading into are these, or maybe it's the second one, I'd have to look it up. And then for your add and NAND, it's the other set of bits. Determine which register you are writing to. Also keep in mind that these instruction bits are being forwarded back to the register file to enable writing. And that is it.
Bless you. Bless you.
What about the program counter? Oh, no, we don't worry about it.
Not yet. We'll get to that. That's a great question. So it looks something like this.
Whoa.
Blue lines.
You have fetch, store it off, decode, store it off, execute, store it off, memory, store it off, complete the instruction.
Branch isn't good.
How's it going, David? Good. So let's see, an easy test question. Which item does not need to be included in the memory write back pipeline register for MIPS 32 pipeline implemented implementation discussed in class. There we go.
PC plus 1 plus offset.
Why?
Because it's
Because
not
we
the
don't
last
use
part.
it.
You got rid of it in the
Okay.
part 4.
Yay!
Here's a hard one. What
Oh,
items
man.
need to be added to one of the pipeline registers discussed in class to support some nasty instruction I decided to come up with to see if you know what's going on? Just be ready for that question.
Okay.
I'll replace this with an instruction that makes sense.
If you replace that with insert nasty instruction description here, I would be upset.
Be quite put out.
Yeah. Be quiet.
That should be one of the answer for that.
All right.
Instruction.
Things to
Put
think about.
Put out.
How would you modify the pipeline data path if you wanted to double the clock frequency? Well, let's go back, actually.
Oh, you split it up more.
You split it up more. Right. So what determines your clock frequency here?
The clock of each
Well,
biggest
clock of the
cycle.
longest.
yeah, the longest one. So
You split it up.
you split that one up, cut it in half. Is your clock rate going to double?
No, it's going to shrink.
Sure.
Well, right,
It's gonna
well,
get better.
It's going to get better, but is it going to double? Be half your clock? You're thinking your clock time will be halved. I'm saying your clock rate will be doubled. Is that actually going to happen? Your clock frequency, or
No.
why not?
Because we'll just take the
Yeah.
longest next longest instruction.
Yeah, because the next longest one is now going to determine.
So you have to divide them all.
Yeah, you have to divide.
Divide and conquer.
Split it up into 8 parts.
Yep. And then how do you determine the frequency? Great.
32.
Okay, hold on a second.